back about direct and indirect testing. Most of our testing, whether we are looking for IgG or IgM, whatever, if we're doing a serology-based test, most of our testing is going to use an IgG antibody. I would say probably greater than 90% of monoclonal antibodies are IgG, just because they're easy for cells to crank out. They have a simple structure, which means inherently copies of them are going to have less problems. You know, if you're reproducing something very, very simple, it's a lot easier to make them very uniform. If you've got something like an IgM molecule that's much more complicated, there's a lot more places where there are. Yes.
Sorry.
Yeah.
So, when we make antibodies, do we always make a G, M, and maybe a D? Or
You always make M, you always make G. Sometimes you make D, sometimes you make E. But no, you do always make a D. I'm sorry, there is always a D. It comes in between the M and the G. You've got M, and then you know where G starts? Somewhere in there, you've got a little blip of IgD.
A and E would be more specific to what is.
A is not generally, it's a specific antibody, but it's just kind of made and put into your secretions. It's not necessarily produced in response to a disease. It will, if it recognizes an antigen, it will stimulate production of more antibodies to that particular disease. But IgA in a pretty much unspecific form just floats in your secretions, just looking to attach to anything that might come through. So I don't want to confuse you and say that it's not specific against an antigen, but it's kind of hanging around like a blank canvas. And it just kind of hangs in your sweat and your tears, and so when things get in there, it's like, ooh, look at that! I can make an antibody against that. So it is just kind of continually pumped out. And you have some people who are what we call secretors, and some people who are non-secretors. People who are secretors have IgA in their secretions. People who are non-secretors do not. And I don't know why. I don't know the mechanism for that. And frankly, I got a lot more to worry about. So someday, I'll put that on my list of, someday when I have nothing better to do. I'll look at it. And please don't be afraid to ask questions, because and if I don't know the answer, I'll tell you the answer. All right, precipitation reactions. We actually don't do a ton of these anymore, just again because a lot of our methodologies are becoming more sophisticated. Although we don't do a ton of agglutination on the little card anymore, but we do 10 times as much agglutination reactions as we used to, because a lot of them have been automated. So a lot of our automated systems find that doing an agglutination reaction works very well. So like our LEA test on our Stago that uses a latex particle and just looks for the light to come through. Same thing with precipitation. A lot of these are not manual, but some of them are automated, which makes it a little difficult sometimes because you don't actually see it when you're doing it. Just like a CBC. We have you do a manual CBC. You have a picture in your mind for the rest of your life now, that little hemocytometer. Okay, you will have that picture, and it makes a CBC and it makes your blood counts something you can kind of visualize. Okay, if all you're doing, or like when you do a manual chemistry, you remember, oh yeah, we had to pipette that in there, and then wait, and then pipette that in there, and then wait, and then pipette that in there, and then mix it, and then put it in the spec, and you get that visualization going in your head. Those manual methods still are a great teaching tool, because otherwise, all we're churning out is button pushers. That's society. I can push a button. That's nice. But if you know what's going on behind the scenes, it makes you just a wee bit more valuable. because it helps you with your troubleshooting. Okay? So precipitation is one we don't do a whole lot of, but except if you're using something called the nephelometer, or we have a couple other analyzers that use it. In precipitation, what we do is we have a soluble antigen, which means it dissolves. Can't see it. We have a soluble antibody. It dissolves. You can't see it. When they hook together, they produce an insoluble complex. Now, for the most part, yes, these are visible, but for the most part, they're not visible to the naked eye, at least not discernibly. Occasionally they'll get that strong, but for the most part, they're a very, very mildly hazy solution, okay? So reading them is usually going to require some sort of instrumentation. Initial or antigen and antibody reactions, there's a couple of terms that are associated with it. The first is affinity, and affinity is simply they like each other. Oh, isn't he cute? Okay. Affinity means I like that guy. I like that girl. Okay. It's that initial force of attraction that exists between the FAB site of the antibody and the epitope or determinant. Okay, an epitope and determinant mean the same thing. And the epitope site on the corresponding antigen. The bonds dissociate and reform continually to better fit, okay? So they basically, you know, they can form, it's like, okay, I got, no, wait a minute, no, okay, there we go. We got a nice strong bond, okay? So it's kind of like trial and error, trying to get the key in the lock and you're not quite getting, you gotta fidget it a little bit, okay? So they don't always go together. They don't always hook up nice and smoothly. We have a variety of non-covalent bonds that hold the antigen to the binding site. The first ones are simply an ionic bond. And we talked a little about these when we talked about using LIS. And does anybody remember what LIS is? What does it stand for? What does LIS stand for?
Low ionic strength saline.
Low ionic strength saline, or low ionic strength solution in some cases, what do we say? But yeah, low ionic strength saline. And what does it do? It decreases the electrostatic charges so things can get closer, okay? So that works with our ionic bonds. Simple electrical attraction of negative and positive. Once we've got them sort of close enough together, they start to make more bonds. The first is a hydrogen bond. This is an attraction between the polar molecules with a slight charge, or a slight charge separation, where the positive charge resides on the hydrogen atom. So my positive hydrogen atom finds a negatively charged something on the protein, and it forms a hydrogen bond where the hydrogen shares an electron with the negatively charged particle, because hydrogen atoms that don't have enough electrons get very hungry, and so they will go and they'll sort of, you know, catch a ride on the back of anything that has an electron. Hydrophobic bonds occur between nonpolar molecules that associate with one another. The important part about a hydrophobic bond, water hating, okay? So this is a non-water based bond, okay? It will kick out any water. It forms a bond and excludes any water that might be around. Van der Waals forces, these are forces that are between any two molecules. You've got the electron cloud around this molecule, the electron cloud around this molecule, and they just sort of are attracted to each other, okay? Sort of share the protons. This is just, all of these are extremely, extremely weak bonds. They only occur if you get them really close together, okay? So we need the perfect lock and key for maximum affinity. What these guys kind of do is they're kind of, you know, I like that girl, okay. Oh, so they'll introduce them so they're next to each other, okay. They get them close enough that they can start to interact on a deeper level and form a much stronger bond, okay. So these guys are just kind of the initial, hey, how you doing? Okay, just getting them close enough that the interaction, the real bonds can form, the tighter bonds can form. Avidity is basically how close together they are and how close they have to stay. It's all of the attractive forces between the two things, the stability of the complex. If the complex doesn't stay together, we can't measure it. It's very hard to measure things that, you know, imagine trying to, you know, count cells that disappear and then come back. Okay, we gotta have something that stays there so we can measure it. Avidity is how closely they stay linked once they're linked. Okay, what we want high avidity and we want high affinity. That's the best for keeping these molecules together. High avidity can compensate for low affinity. You know, if you live in a little tiny desert island and there's not a whole lot of people there, even if, you know, the girl next door ain't the most attractive thing on earth, well, she's all you got. So, well, you can overcome that. I'd like something more attractive because, well, she's here, you know, and it's better than nothing. So if you can get something where you have a very high, a high avidity can compensate for the fact that they're not the best match that you could find if you were sort of to go outside the area. I know, and it's not the greatest analogy, I'm working on it. Zone of equivalence. This is what we've talked about, prozone and postzone, and I bring this stuff up multiple times for a reason, because this stuff's important. So zone of equivalence is where you have the correct number of antibodies and antigens to react in the correct proportions to give you the result you want. We've already talked about prozone when we talked about agglutination. And yes, I know I've talked about it before. I'm talking about it again. Hint, it might be on the test next Wednesday. Maybe, perhaps. So, prozone is when I have an antibody excess. They don't have to share. Okay. So if I'm in the precipitation, in the agglutinations, it has to pull the pieces together so I can see them. In the precipitation, it will be able to see the individual ones, but it can see them better if I can make more lattice-like structures. If I can put a bunch of them together, it's going to be a lot easier for it to see. Okay? I'm going to get a weak reaction or a false negative reaction just because I have so much antibody that nobody has to share. And that's why a lot of tests that we do, we start with a dilution. When you did your, you did D-dimers, do D-dimers dilute to begin with, or you do a straight for the first one. Think FDPs dilute for the first one. But there are some things where you make a 1 to 10 dilution and you run the 1 to 10 dilution. Because if you run it straight, you risk prozone. And those things are developed, those things are decided as they develop the test. So when the test gets to you, it's going to already tell you, oh, you're going to make a 1 to 10 dilution. Okay? Because somebody in a lab started with it at 0, and then went 1 to 2, 1 to 4, 1 to, you know, and did varying dilutions to find that sweet spot, that zone of equivalence. Post-zone is the opposite of prozone. We don't see this nearly as commonly. This is more a bad test design. It does happen in some cases, but for the most part, this one we don't see near as much. If I'm looking for antigen, It can happen that I have so much antigen that, again, my antibodies don't have to share. They can have their very own. There's plenty of antigen for each one to have one or two. But it is not as common as prozone.
How does it present itself?
The same,
Prozone is like negative, 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 positive stuff.
you'll have the same thing. Same thing. It presents itself, except that in prozone, we're looking at antibody excess. In postzone, we're looking at antigen excess. And just frankly, most of the time, we see prozone. Most of our kits that are measuring for antigen are designed to dilute out if, and most people don't have enough antigen, so it just doesn't happen as often. But it can, and it. All right, precipitation in solution. Nephelometry, it measures light scatter, okay? Do you remember the flow cell cytometer, the optical testing we used to do white cell counts in an analyzer? Smile and nod, okay? And basically we passed things through it using laminar flow where we made the fluid keep going so it was too hard for stuff to swim back upstream. This is pretty much what we do here. Same kind of thing. We're going to put this through. Depending upon the methodology, it's either a pass-through reaction, which is what we do in a flow cytometer, or a static reaction, where we let it react and then we bring it in to the measuring well, read it, and take it out. So does that make sense? That in a flow cytometer, it's a pass-through where it's going through constantly. Most of these are more it pipettes it into the cuvette and then just measures through there. But it looks for the light scatter at an angle. And depending on exactly what you're measuring, you may look at different angles. Okay? Or you may look at all of the angles. Or you may look at 40, 50, and 70. Yeah. Again, these types of parameters are worked out in the lab in the research lab before these things ever come to you. So the amount of light scattered is directly proportional to the concentration. More stuff, less light. Okay? More stuff, the light gets scattered more. It just makes sense. If it's a perfectly clear solution, nothing's going to stop the light. If it has something in there that's going to bounce the light off of it, you're going to get an increased scatter. The methodology most commonly is used to quantitate immunoglobulins, complement, and CRP. Any more pretty much complements it. Obviously, there's always going to be a few things. Immunoglobulins, we've got a lot more tests that can measure those. Frankly, what we do is make anti-immunoglobulin antibodies and use those in an EIA test on the analyzers for the most part. CRP, because it for a while it was like the golden child of everything and it was going to solve all of our problems. CRP can be measured a wide variety of ranges, or wide variety of ways. So most labs just don't have a nephelometer anymore. Or if they do, it's built into something else. I believe there is one instrument on the market that does chromatography or spectrophotometry, the EIA, and I think it does have a nephelometer on it as well. Where basically you've got a big pipetting module that does all your pipetting, and then it sort of sends it off to whichever one's going to read it. Radioimmunodiffusion. This one's kind of fun, and we're going to do it just because it's kind of fun, and it takes up a whole lab. So anyway, but it is one that is still done a little bit. Oh no, we're going to do octoromy. Radioimmunodiffusion is very, very simple. What we're going to do, we pour out an agar gel, and that's just like you would plate stuff on. We just don't put anything in the agar. It's just plain agar. We pour it out, and we use a highly advanced method to make little holes in it. It's a plastic straw. And you pop out these little wells. And what you're going to do is you're going to apply the antibody. The antibody is going to be in the well, in the auger. The antigen is going to be applied to the wells and allowed to diffuse. The rate of diffusion depends on the antigen concentration. Basically, if I'm looking for an antigen, I'm going to put antibody in my auger. If I'm looking for an antibody, I'm going to put antigen in my auger. Then I'm going to put varying concentrations of patient sera in the little well. I'm going to let it sit for anywhere from 24 to 48 hours, and I'm going to see how big my precipitation ring gets. In case you can't figure it out, doctors really don't want to wait 24 to 48 hours for a semi-quantitative test. There are a few things that they will still use this for, but again, it's just not used a whole ton. Mostly you're going to see this in a reference lab. The tech time involved, the imprecision of the methodology itself, we just don't use it very much. Now, you'll find sometimes the really weird tests, the things you don't measure very often, a lot of times they'll use these older methods just because they're simple, they're cheap, compared to trying to develop something that'll go on the analyzer. If I'm only going to do, 50 of these in the country this year, then I don't really need a high throughput, quick turnaround time kind of thing. Okay, and just like with anything else, we set up a standard curve. We take something with known concentration, figure out where it's going to plot on the graph, then we plot our unknown and try and figure out where it falls on the line. Okay, and that's pretty much any method you do that you set a standard curve for. Okay, so basically here, what you would do, your low standard, your medium standard, your high standard, and your patient. You're going to run them, then you're going to measure, then you take the square of the diameter and you plot it on this lovely little graph. Okay. And the line does tend to bend. It's not going to be necessarily a perfectly straight line. And then you just figure out where your patient falls and go read it off the graph, just like you did when you did manual hemoglobin readings. If the ring is greater in diameter, well, quite frankly, it doesn't matter what test you're doing. If your measurement is above your linearity, what are you going to do? Dilute it. Whether you're doing chromatography, whether you're doing flow cytometry, if it's above your linear limit, you're going to dilute it. Okay? So you may do a 1 to 2 or whatever, and then you're going to rerun the test. And then when you get done, you multiply by your dilution factor. That is, okay, yeah, this is radioimmunodiffusion, but does it really matter what test we're doing? This is what you do. If it's too high, this is chemistry in a nutshell. Put it on, push it to button. Oh, it's too high. Dilute it, put it back on, push it to button, multiply the result when it comes out. Okay, pretty much straightforward, no matter what testing you're doing. If you're outside linearity, can you report it? No. Unless you report it as greater than or less than. Okay. And in some cases, basically the doctor isn't going to care. If it's greater than 150, doesn't matter whether it's 170 or 309. No, it's just high. You need to deal with it. Okay. So those are decisions that are made on every test, no matter what you're doing. Basically, the biggest sources of error are not pouring the auger correctly, overfilling or underfilling, because you need a standard thickness, because this immunodiffusion is not going to be occurring in a 2D, it's going to be occurring in 3D. So if it's too deep or too shallow, it's going to change your diameter because you're going to get a volume, not a distance. If you fill it and you accidentally put a little hole or nick the side of the well. Have you guys plated anything on auger yet? Okay. How easy is it to plow up the auger? You
It's
Farmer
really-
Joe. Oh man, look at that. Yeah, it's real easy. That stuff is not. I mean, it's really not even as tight as Jello sometimes. If you nick the side of the well or you scratch the auger while you're filling it, it can cause an unusual form. Obviously, if you don't do the test right, it has to be at a certain temperature, it has to be at a certain humidity, and it has to be for a certain period of time. If you don't follow the test parameters, the test isn't going to work. Duh. Yes.
Is this auger specific to the rig or RID? Or can it be, is it used for something else? Do you always? pour
Auger is just the gelatin-like substance, and
There's different
this
ones.
particular auger, if I'm doing, let's say I'm looking for the C3 component, okay, I'm going to have an auger into which I have added anti-C3.
Okay.
I know I said you're not gonna put anything in it earlier. What I meant was it's not gonna have blood or that kind of, you're not gonna have nutrients in it. You're just gonna put the antibody in it. So yeah, it will be specific to this particular test. Yeah, so picking up the wrong plate would screw that up too. Reading off the wrong graph would screw that up. So basically screwing up the test will screw up your results.
So you
Yes.
say you have to actually make that gel stuff?
You can I imagine you can buy it from Rimmel. They probably make it.
Okay.
Yeah.
I was wondering, I seen them
find
already,
recipe
like they
online, too.
have like different augers.
Yeah,
So
that
we're
we
like-
order most of them. These RID tests are fairly uncommon, so I don't know. It would depend. Some places make their own. We're gonna make our own just because it'll keep you busy and it's fun. And with Halloween coming up, if I have some leftover, okay. Again, precipitation reactions in gel. Most of our precipitation we measure on the nephelometer. Manual methods are going out of vogue a lot, and why is that? What? Human error for one. Cost is a big one. You know, when one of your biggest costs in the lab is your people. So if I can get an instrument that can do 100 of them in an hour, and it takes up people, can do 10 of them in an hour, you know, and my people cost a lot more. You don't have to have health insurance for your instruments. They don't need a day off. They take them once in a while, but they don't need them. When we're doing the octolony, and this is what we are going to do this one in class next week, it really is not that difficult. We're going to take the gel, the little, we have cute little petri dishes here about this big. Okay. I'm gonna put my antigen here. I'm gonna put dilutions of my patient, or different patients, or whatever, I'm looking for antibody. And what's gonna happen, the antigen is going to diffuse out this way. The antibody is going to diffuse this way. And what we're gonna get is we're gonna get a line where the two of them meet up. Okay? Then based on that line, and I would pay attention because y'all are gonna have to be able to draw this. This one they still do use for fungals. Again, one of those things they don't measure very often, and it works pretty good for fungal. So basically, antigen here, antibodies here, and we're gonna see those precipitation lines. And those are nice, lovely, dark, beautiful lines. Never. They're more like a little fuzzy kind of, sort of thing. Okay, you gotta look real close, you gotta kind of angle it just right.
Diane, that looks like 3 different lines, but there's 6 different wells there, so did 3
Well,
of them
we're
react?
getting there, hang on. Okay. What we're doing when we're looking for the thing, if my lines go like this, okay? If I bind with one and not the other, this is identity. If the two go like this, everything is bound, and I have full identity. Okay? The antibodies in each of the outer wells are identical, and I have that this is whatever antigen I'm looking for, antibody I'm looking for. Non-identity, okay, identity means that as the antibody's coming along and the antigen's coming along, they match, so they join up and they precipitate out. In non-identity, they meet up and they don't like each other, so they just keep right on going. And they keep diffusing, okay? So, this is identity. This is non-identity, where they cross like that, okay? You will not be expected to draw this till after we do this. So, thinking Tuesday, we're gonna do this one, because it's tedious, it will take quite a bit of lab time. Okay? Partial identity. When we do this test in lab, our non-identity usually works real good. Our identity usually works real good. Our partial identity, yeah, it sometimes takes a couple days, literally, for us to get our partials to come up. Okay? Once we do it, and I will go over this as we are doing it in class as to what's in each well and what's going to come together, I think it makes more sense when you're hands-on with it. Okay? But you will need to be able to draw partial identity, identity, and non-identity. Yes?
What's the 1, 2, 4, and 8?
That's just the dilutions. Yeah, you can put different dilutions, you can put different antigens, different patients, there's a variety of things you can put in those wells.
Why would you get different solutions if you're just looking for when they meet up and react?
See which ones give you the strongest reactions. Sometimes, again, prozone, post-zone, making sure that you've got an ideal combination.
Would it be happening just once up there, or would it be in between all four?
It's usually in between all of them. I just am lazy and don't enter.
And you can put the antibody in the middle as well, and antigen on the outside?
Correct. Yeah. As a matter of fact, when we do our fungal ones, which is the only one we ever did in lab, we don't do them anymore. We do complement fixation for those instead. But what we did for those was we had coccidioides, blastomyces, aspergillus, and whatever that other one was that I can never remember. And then we put patient serum in the middle, and we looked for it. So like if it made a line here, here, it would tell us which ones we had.
So it's not the same.
Again, is this one you're probably ever going to do?
Would immunoelectrophoresis be what's replacing this?
No, complement fixation's what's replacing this. This one, we still do. This is probably the only precipitation reaction we actually still do. And it's not strictly precipitation. It's electrophoresis. And I know Barb talked about this with you. But basically we put it on a gel just like hemoglobin electrophoresis, like any other electrophoresis. It's a gel plate. And you take a piece of paper and you dip it in an agar gel and let it dry. So you just have a very, very thin layer of agar on the outside, although they have some newer latex and other medium that they use instead of agar, just because agar is too easy to scratch. So there's a variety of different types of gel you can use. But you just put it on there, you put an electrical charge through it, and basically your albumin is going to drop out first because it's the heaviest. Then you're going to go down to your gamma, and then your gamma is where all of your immunoglobulins are, hence the name gamma globulins. This is where all your immunoglobulins are, and then what we can do if we want to see that particular section more closely, we'll do what we call an IFE, which is an immunofixation electrophoresis. And what that does is we add an antibody onto the gel that is against antibodies, and we let it precipitate out, and you'll actually be able to enlarge this particular area where you can see just where the antibodies fall. Okay, that's lovely. Am I gonna ask you to interpret electrophoresis? No. Did Barb ask you to? Well, that's her. Again, okay, sources of error, overfilling or underfilling wells, incorrect buffer of the pH. If it's not exactly on, if your pH is not perfect on your electrophoresis, it's really gonna mess with things. Pretty much, once again, if you don't do the test right, you're not gonna get the right answer. Okay, fairly straightforward. The proteins aren't gonna move if I don't have the correct polarity in the gel. If I don't have the correct voltage, the proteins may denature. And what denatured protein is, it's cooked. Okay? Incorrect electrophoresis time, I looked at it go too long or didn't let it go long enough, so they aren't gonna migrate the way they're supposed to. Basically, I didn't do the test right. You guys talk about Bence-Jones proteins. These are our kappa and lambda chains. This is probably, and we still do electrophoresis quite frequently. Memorial still does it, hopefully not much longer. Just because we don't do enough of them, and it takes like a whole person a whole day. So basically the proteins can be separated in the same way that serum proteins. You just gotta kind of put a little more in there or concentrate it out. So when we're doing a urine electrophoresis, we actually have to concentrate the urine. We have to send it through a special filter and spin it down like forever. So you'll spin 40 or 50 cc's of urine, and when you get all done, you'll have maybe 100 to 200 microliters of sample, because you just concentrate it down as far as you can, so you have enough that hopefully that it'll come up on the electrophoresis. Occasionally we'll find kappa and lambda free, kappa lambda chains. These are Bence-Jones proteins. Most commonly we find these in cases of multiple myeloma. We will also find them occasionally in Waldenstrom's macroglobulinemia, but mostly the Bence-Jones come up in multiple myeloma. This was the screening test of choice for quite a long time for multiple myeloma patients, until we came up with much better screening tests that did not involve 24 hours of urine. We frequently found, for some reason, one of our orthopedic doctors ran one of these on practically every patient they worked with, and we would find multiple myeloma a lot of times just by accident, just because the doctor decided to do this test on everybody. Just because you have free kappa and lambda chains does not mean that you have multiple myeloma. Immunofixation, electrophoresis, we already talked about this. You apply the antisera onto it and look for precipitation. Western blot. This methodology is used to confirm HIV-1 antibodies. They still do this. This is a send-out test. You're not going to do this pretty much unless you go work for a specialized reference lab. This isn't one you're going to be seeing, because this thing is massively a pain in the butt. A lot of tech time involved, a lot of specialization in being able to read the results involved. Basically what we do is we electrophorese the HIV antigen to separate out the pieces of the HIV. So the first thing we do is we take the patient, we treat the sample to release the HIV virus and pound it into pieces. We then put it on an electrophoresis to separate those pieces into parts. And then we put that onto a blotting, a nitrocellulose paper, which is a blotting paper. We apply the patient's serum, which contains antibodies. And after we put the patient's serum on there, any of the pieces and parts that the serum attacks or reacts with are going to precipitate out then we apply a stain, and if we see any little staining lines, we know that they have antibodies to HIV. And there are dozens of HIV antigens that you can make the antibodies against. So this Western blot checks to see, and you have to have, I believe, 2 of the, you must have, I don't think it's still 2 to 3, I think you have to have more than that these days. But you have to have some of the antibodies, not just one, because there could be a cross-reactive antiviral antibody to something else. So you have to have 2 or 3 before they'll call it positive. This is the most important one that we're looking at here, and you might want to circle this, is the anti-P24. This one was very important to the US blood supply, okay? Because we have created, and they don't do it by Western blot, they have a different method, they have created a test where they can test for this P24 in the blood. They test for that antigen, not the antibody. They test for that antigen to see if there's any HIV in the blood supply. So this is what they now test humans with, is the P24 antigen test instead of the antibody test. But that is the confirmation test. So if you get a positive HIV screen, you then have to do the confirmation.
What are other, Western blot tests, like, more popular? I feel like there is-
That's the only one that's the most popular. If you're sending out a Western blot, probably 80% of the time it's HIV. There's others that are done by that method, but I don't know if they are off the top of my head. And I know there was one we sent out that was a Southern blot. I'm like, seriously? They're pretty much all viral antigen antibody tests. That's as specific as I can get. There's a Southern blot? What's the difference? Maybe it's the way the gel goes. I don't know why they're called that. All right, questions? There's a class comes in here at 9, am I right?
I don't think on
Thursday.
Thursdays.
No, on Thursday. See, I can't even keep track.
Notice how we all said think.
Think,
We can't
yeah.
keep track either.
Well, I'll tell you what, why don't we take about a 15-minute break? Then we'll move on to labeled immunoassays. If there's a class in here when you come back, go across the hall. So have your stuff packed up in case we have to move in a hurry.